I'm going to try not to kick off the feedback. Sorry if I do that. So, hi everybody, I'm Matt Gorton. I'm going to talk about the intersection of design, process, and materials. So, considering those three things and putting them together to end up producing a better outcome, a 3D printed part that's stronger, more functional, that gives you more of the results of what you're looking for. So the agenda here, so I'll introduce myself, I'll introduce my company. I'm going to talk a little bit about how this event started, because I was there where it was conceived. I'm going to talk about this idea of a new design paradigm for 3D printing, some things you should think about when you're designing that you may not be thinking about now. And then I'm going to get really into the meat of the presentation, which is we're just going to talk about just a few examples of how you would apply some engineering fundamental concepts to 3D printing to kind of improve your result. And the talk before mine was an absolutely perfect lead-in to what I'm going to talk about, because I'm going to be talking about the strength and the structures that he talked about there. We're going to talk about how that's meaningful to your prints. And then I have a hands-on sample. So I'm going to pass that around first, and I will set the microphone down here so I don't make feedback. Turn it back on for 1 second. I want everyone to take one black sample and then one of the paper-backed samples. And the black samples, we just made them before we left, and they're dirty, so don't rub your fingers on them a lot. We're just going to break them and throw them away. But wait until I tell you to break them. All right, so just talking about me a little bit, why I'm doing this, what my background is, where I came from. So I'm a mechanical engineer by education. I have my master's of engineering in mechanical engineering and kind of focus on materials. I've worked in the medical industry, medical devices, aerospace, automation, just a range of different things. And then about 5 years ago, I found this desktop 3D printing stuff, and I went ahead and started a company. And my wife and I, one night we discovered, I had used 3D printing in my job for years, but I wasn't aware of the desktop machines and the RepRap movement. And so I discovered it. And as soon as I discovered it, the next day I started a company, because that's, why not just start a company for running things instead of just doing it for fun? And bought a printer. My wife and I came up with the name Printed Solid in 2013, and that was that. My passion kind of starting out was this idea of, in 2013, those of you guys that have been doing this for a while, a lot of the materials that were around then were really, really, really bad. And it wasn't just the cheap ones that were bad, it was the higher end ones that were bad. So I had filaments that I bought that had certainly diameter variation. Everything you bought had design variation then. I had filament that had wood chips in it, metal chips in it. People talk about clogging their extruder now, but it's, you find metal shavings in there, and that was a good time. I think my favorite was finding filament that was actually glued to the side of the spool. That was awesome. And then another one was filament that on cardboard spools where the cardboard wasn't strong enough, and the filament would pull off to the side and then down to the bottom and then jam during your print. And like when Protopasta came out with their cardboard spools, I know I gave them a lot of feedback, like, don't do cardboard spools because that's going to happen. But clearly they've solved the problem. But, lots of things have happened. So my passion on, why I started doing materials was, one, it's a background. And then two, I just wanted to find sources to bring better materials to this market. And I feel like I've done that. We're now kind of changing a little bit. We're a little bit less niche. 2016, I made the jump of quitting my day job and opened a physical building for Printed Solid. So, you go about an hour up the road and we have a 3D printing store. So you can come into our store and you can buy filament. Now it doesn't really look that much like a store. It kind of looks like my messy office and workspace, but everything's there. You can come in and you can buy stuff. Whatever you order online, you can go buy in the store. We give you a discount. I love this. I love this RepRap thing and all you guys and like everyone just being into this and talking about it. And so because I have my own building, I can have my own kind of mini little baby RepRap Fest. So about once a month, once every couple months, we do these Sunday meetups and people come in and it's kind of like a teensy tiny miniature version of RepRap Fest. So if you're in this region, I'd suggest that you check that out, come to the store, hang out with us once a month. Yeah, so then in 2013, a friend of mine, David Randolph, who had his own business called Rand Laser, did laser cutting. We merged it, and now we're kind of expanding and doing more things. So let's just talk about, and then I'll get into the presentation, but I just wanted to give this little bit of background. So 2017 Midwest RepRap Fest, Chris, Don, Ron, who I believe is here but ended up pulling out, and then Lauren and Nick, we had breakfast together. So ERRF was born out of a group of people who happened to be staying at the same hotel, having breakfast together at MRF. So if you see these Twitter discussions where people are like, oh, I wish there was a RepRap Fest near me, make one near you, do it. Chris and the team, they did awesome with this. Now, it did help a little bit that I had a really good year that year with Printed Solid, and we had a little bit of extra money, and we could say, well, you know what? We're going to cover the costs, and hopefully it's a hit, and hopefully we're not throwing this money away, but whatever. We're going to do it. We want it to happen. So we did that. East Coast event, everything's expensive here. Everything's more expensive. Those of us that are in it, that are sponsoring it, that have kicked in, it was a great thing to be able to do. I'm proud of that. So, make sure to support us for sure. Make sure to support the other sponsors. It's a pretty serious commitment to community to invest in a first-year event like this that you don't know if it's going to ever do anything. So now on to the actual presentation and what will hopefully be interesting to you. So as I was preparing this presentation, I kind of structured it as these things are your process, these things are your design, and then these things are your materials. And I found I was often having a hard time with which things goes into which bucket. And it occurred to me that when I slice apart, it's not like I'm running a injection molding line or an extrusion line where I'm designing a process and I can kind of follow these fundamental rules and the process is the process. When we slice apart, we're continuing to define the structure of the part. So, typically you think of a machine part or injection molded part where the outside of the part is what it is, the inside of the part is solid. We all know that our parts are not solid on the inside. We have lots and lots of variables. So I just wanted to, point this out that when you're slicing, you're not just pushing a button. A lot of people want to have pushing a button. I don't think it ever can be because slicing is design. So you leave CAD and then you sit down at your slicer and you're continuing to design your part. So it's just something that occurred to me as I was preparing this. So keep that in your head. Think about it as you're doing things. So stress concentration. So the previous presenter, and I found this incredibly interesting, talked about the internal stress concentrations inside your part, which entirely ties into this concept of your slicing parameters are part of your design. But I'm going to talk about this as being one of the major concepts here that really matters a lot for your design and for the strength of your design. And that's what these pieces are that we're passing around. So a stress concentration defined is any point in an object where the stress, so the stress is the flow of forces inside your part that cause it to break or deform. It's any point inside an object where the stress is multiplied. So any place in an object where you have an abrupt change in geometry, like a hole or a slot or a ledge or something like that, any point where you have that change, you have a stress concentration. So what I want you to do here is take the acrylic sample, which is the one with the paper, and hold it in your hand. Hold it in your hand like this. Thanks, Don. All right. So hold it in your hand like this, and then take the sample that has the sharper radius, or the sharp thing with no radius, and then break it. Really, really easy to break, right? Now go to the other side where we have the fillet put in there, and then try to break that. A little bit harder to break. It broke away from the radius. So that's just a design consideration. So that's meaningful for any physical object that's being designed. It doesn't matter if it's 3D printed. We're talking about 3D printing, but that's relevant to any design. So if you look at most real things that are designed, most of the corners are rounded in some way. That's why. When you round the corners, you get a little bit of strength added. So in your design, as you're designing things, this is really simple. Put fillets or chamfers at all inside, outside corners. I goof this up a little bit. It should be, generally, in vertical planes, your chamfers. So a chamfer is where you have like a 45-degree angle coming off the material. A chamfer is generally easier to print than a fillet, which is a radius. So fillets usually look nicer, but chamfers are easier to print. So consider that when you're designing. What's your part? Who's going to be looking at it? If you're making a ton of them and it's just a structural part and you don't care what it looks like, put fillets around. Put chamfers around. If it needs to be a little bit more cosmetic, maybe you need to put in some of those, fillets, those nice rounds. But don't leave your corners as just being 90 degrees, because one of the other things, if you think about it with FDM printing, that you can't do with a lot of manufacturing processes, you can really truly make a 90-degree corner, a nice sharp 90-degree corner. You go from layer 1, and then if a tower starts at layer 2, you have a 90-degree corner there, and you're going to have a huge stress concentration. So that's a very, if all you remember out of this talk is to put fillets and chamfers in place, you'll have increased your strength of your parts by 100%. So now remember this, again, your process is your design. And I feel like I don't even need to talk about this, because if you were at the previous talk, there was the tensile test where it shows the stress concentrations at the point where the layer lines hit the walls. So that's showing that inside your part in FDM printing, you have these internal stress concentrations. That's for a 100% infill part. Now you take our parts, which most people don't print 100% infill, and okay, all right. So it was exactly this, right? So you have your not 100% infill part, and you're getting stress concentrations at the edges. So think about that inside your part. A lot of people say, "Oh, I'm going to put 50% infill or 70% infill inside my part, and it's going to give me strength." But realistically, you're giving all these junctions and transitions, and you're creating all this internal stress. So consider that. The other thing to consider is there's so much going on in our process. An FDM part is like just a big stress concentration. Your layer heights are stress concentrations. So you have big beefy layers where it's nice and ridged on the surface. Looks kind of, for those of us that do this, that love 3D printing, we kind of think it looks cool, but those beefy layers are giving us stress concentrations. Layer width is meaningful. When you have a rough overhang or a bridge, it doesn't just look bad. That surface is disrupted. You're multiplying your stress there. Yeah, and that's just the stuff that you're seeing on the outside. Those of you that have watched time lapses, which is probably all of us, and watched our parts printing, we know that during the print, there's all this garbage happening inside of the print as well that's creating stresses. So you really have to think about, when you're designing your part, and slicing is part of your designing your part, you have to consider that. Yeah, so then just kind of talking about materials broadly and specific to 3D printing, but not necessarily only specific to 3D printing, is this notch sensitivity concept. So now we look at our black part. So materials that are ductile, so materials that can bend a little bit before they break, are less affected by these stress concentrations that are materials that are brittle. So that acrylic that I passed around, acrylic is well known as a brittle material. You know, those of you that have printed your own machines or bought, you know, a cheap overseas machine, or even, you know, that's not fair. Cheap machines in general that are using acrylic frames. You know, experienced rep wrappers are going to say, don't ever, ever, ever use an acrylic frame, except for the big box, which was an exception somehow. Because acrylic is a brittle material. It's a fairly strong material, but it's brittle. So you bump it, you drop it, you know, you have your print gets knocked off the bed and is getting, you know, kind of whacked against the side of it, and it's going to break. So these, you know, stress concentrations in a part are more meaningful for a strong brittle material than for a relatively weak ductile material. So Don, you want to do the microphone again? So if we just do the same experiment again, so apologies again that you're going to need to wash your hands after this. You can blame Dave, my partner Dave, even though it didn't be an awesome favor in running these last minute. I'm still going to throw him under the bus. But yeah, so take it, hold it in your thumb so you don't cut your hand, and then take the sharp piece and then bend it and try to break it. And you'll notice it's going to bend a lot before it breaks, and then it's going to break and it's going to go. Okay? So now this is where I think it gets really interesting. Now take the other one, the one with the radius, and now take that and try to break it. And so you'll notice, if you remember when you broke the acrylic piece, it was like you're bending, it takes a lot of force, and then it just goes violently. Whereas this just bends right away, you know, it's not really resisting me at all. But then when it breaks, it's like, you know, it's almost, I bend it almost 90 degrees before it started to give away. So this is our perennial PLA, ABS, any materials, which is stronger? Why can't I go to vendor A or forum, you know, whatever forum, and ask a question about which material is stronger and get the same answer? So now we kind of see why. It's not really that simple. You know, it's not the actual strength that you feel in a part isn't just about the measured tensile strength of the part. It's this interaction of different properties. So then I have one other sort of topic to talk about, and I'm just going to see how much time I'm taking. Yeah, good. Okay. Yeah, I just put this presentation together, so I have no idea how long it's going to take. So I'm going to talk about the two main things. So we talked about the stress concentration, and hopefully that gave you some tools that you can apply to your designs to improve the strength and performance of your design. Now I'm going to talk about this concept of load and stress concentrations. So this is further getting into strength isn't just strength. You know, it's relevant you know, to what the material is, how it's loaded. So, you know, I have an example of a few different types of loading here. I don't know how to use lasers. So the first example there is bending. So that was what we just did with those parts. We loaded them in bending. We bent it until it breaks. So on the outside of the bend, you get pure tensile strength. On the inside of the bend, you get compression. And then in the middle, you get basically no strength, or no stress. Did I say strength? I meant stress. And then if you have a sample that's loaded in tension, so the second one there, so you just have a simple part with a weight hanging off of it, that's a pure tensile load. Same thing in opposite is reverse. If the weight was sitting on it, that'd be a compressive load. The stress is generally evenly distributed throughout the cross-section of your part. Shear loading, so if you have bolts, and you're kind of pulling on them, same kind of thing, it's an even distribution. And then torsional shear, where you have an object that you're twisting. So the stresses are highest at the outside, lowest on the inside. So kind of the obvious thing here is, you know, we go back to this if you if you're aware of how your part is going to be loaded, you design your part so it's beefier where it's carrying the most stress. That's sort of basic, relevant to 3D printing, relevant to designing for anything else. And the cool thing about 3D printing, in traditional manufacturing, in machining or molding, machining, you have more work to do to take out all that extra material, or molding, you have to make a more complex mold. Whereas in 3D printing, doesn't really care. Design what you're going to design it what it needs to be, put material where it needs to go. Consider at those areas of high stress, consider any stress concentrations you have, and be more generous with your features that relieve the stress concentrations. Don't put too much stock in FDM simulations. So, and that's not to say don't do FDM simulations, but it's to just say, be aware that your part is not solid. For people that have done finite element analysis, that should say FEA, not FDM. Yeah, we have too many acronyms. Finite element analysis type simulations. People that do that kind of work. So in finite element analysis is where you build a computer model of your three-dimensional object and then simulate the loading to try to predict what the stresses are. There's a saying in there, garbage in, garbage out. I think with 3D printing, unless you're a very, very experienced finite element modeler, you're probably going to create a model to be analyzed that's not really representative of your part. Okay, so considering load distribution in process. So going back a few slides there, I showed in the bending and the torsional shear that our load is the highest on the outside of the part, and it goes down to nothing or a smaller amount on the inside of the part. So when we say, should I use more shells or should I use more infill? That's to consider that, because there's not a heck of a lot of stress going on the inside of the part. So if you print a rod with 100% infill, all of that stuff inside your part is not really doing much for you. It's just taking up time and adding weight. But yeah, generally, my findings, my thoughts are, in your models, to get more strength, lean towards shells, lean towards making thicker walls versus using more infill. I do think, now we have this gyroid infill. So the cool thing about 3D printing is anytime you prepare something to talk about, it is obsolete 15 minutes later. So, a few weeks ago, there's a lot of buzz around the gyroid models. Not that the gyroid's a new creation, but it's a new option in Slicer that you can use for infill. And I think that's going to be a more meaningful structural infill than anything else. So, something cool to consider. This third bullet down, so under almost no circumstances will it make sense to do something like a handful of shell with a high infill. So that's I did 2 shells and 80% infill. That's generally not something that's going to make sense. So consider that when you're designing. More shells will have more impact for you versus doing more infill most of the time, but prove it. Prove it to yourself. We have 3D printers. We can make things over and over again. Try it. The other thing that I often forget about, and I think I give people sketchy advice when I do classes, don't forget about your top and bottom layers. So when I do classes, I'm in my head, when I'm teaching people about what they should do for slicer settings, I talk about, what's that called when you have the potholes in it? Pillowing, yeah. I think about pillowing when I tell people how many top and bottom layers to do. And I say, do 6 layers. That usually works most of the time. That's all fine for an aesthetic piece, but if you're making a functional piece, your top and your bottom of your parts may be carrying load. So you should make those with a thickness so that they're able to carry that load. Another little bump at the end, and that's perfectly following up on the last conversation, is this concept of isotropy. So our 3D printed parts, and a lot of parts that are made are like this too, but 3D printing especially, your X, Y, and Z properties are not the same. So your part tends to be better in the XY direction than in the Z direction. Now, maybe if we get this thing figured out perfectly with the times and everything, maybe some of that changes and improves. But I mean, it's kind of the nature of FDM is that your Z direction is weaker. And I think most of us know that. But, think about it. I went to, it was a yarn festival. Where they had like sheep and llamas and stuff like that, and it was all about knitting. And to my surprise, I come across this booth there that's full of 3D printed stuff, and they were 3D printing stuff at this yarn festival, and they're actually 3D printing tools for working with the yarn. What was really important there is that it's smooth, but it's also, it's a tool. They're making tools. It needs to be strong. So he's making parts that were just generally cylindrical, easy to print standing up. But he printed them all laying down with supports and had to go sand all those supports off. That is what he needed to do for that part to have the strength that he needed. So, consider orientation when you're printing your parts, when you're designing your slicing. So in going back into the load distribution of materials, I'm going to have to read this. This may have been late at night and it may not make a lot of sense. Yeah, so generally, if you have a more ductile material, it can handle those stress concentrations and distribute things better, distribute your load better. But if your part needs to be more rigid, you can't have a ductile. Typically the ductile materials, not as a law, but generally the materials that are more ductile, that can stretch more before breaking, are also more flexible, generally. Okay, I know what I was getting at here. So this is a little bit of a sales pitch. So, we think about functional materials. You want to have, your nylons. People use ABS a little bit for functional materials, your PETGs. You shouldn't rule out PLAs for short-term functional use materials. So we're going to talk about the period of use in a minute, but for short-term prototypes that don't need to handle the loading, short-term functional objects, PLA is a good, strong material. It's actually stronger, just in pure tensile strength, than most of our options. What I use a lot of are the modified PLAs. We do the ColorFab PLA PHA. Protopasta's doing cool things with their HDPLA, which can be crystallized, which, as we learned, is meaningful as well. We do our Material 3D 850, that can be crystallized as well. Polymaker, Polymax, Matte Forged Advanced PLAs. I get nudged by my team sometimes about we have a lot of different PLAs, but I like using these different materials, and they have meaningful differences and meaningful uses. So consider that. Yeah, so duration of use. So your thermoplastics are, we talk about thermoplastics, which are the plastics that we use, right? Plastics that can be melted and resolidified. We talk about them lasting forever in a landfill. Yes, that's true, but they do not last forever in a landfill where you can pick it up and break it in the same way that you could on the day that it was made. All of our thermoplastics are degrading and changing properties over time, but this is extremely true with PLA, where, I've had PLA, we talk a lot about PLA and moisture, and they say, oh no, my PLA is printing good, not printing well because it's wet, which is not really our biggest concern with PLA. Our biggest concern with PLA is it's not functioning well because it was wet when it was printed or it's extruded, so I lost a lot of my mechanical properties. But that it's wet thing kind of continues throughout its life, so it breaks down a little bit over time, continues to be affected. So your PLA is great for short-term use. Longer-term use, its properties degrade, it's less useful. So I threw out a pitch there for the ColorFab NGen material, because a lot of people look at PLA as it's easy, that's why I'm going to use it, but it has the challenges with with becoming more brittle over time and temperature resistance, whereas NGen's an option for that. So, little commercial. Fatigue loading, kind of same things as stress concentrations. Any that issue becomes more meaningful with fatigue over time. You want to look at the more ductile materials, the nylons, the armadillos, good for that. So I finally have a picture. So we've done lots of words, and I finally have a picture. So creep. So this is another thing that is really, really important for long-term use in polymers. So we make our objects. There's dozens of 3D printers around the room with made of 3D printed parts. A problem with polymers in general, I'll say, is this concept of creep. So what that means is you take your part, you put a load on it, and it deforms a little bit. And then you come back in 2 months, and it's deformed even more. That's creep. So you're not changing the load, but the deformation, the deflection is changing over time. And so here's some examples, not 3D printed parts that I just took off the internet, showing, that first one there is you guys use like heat set inserts in your parts? If you're not, you should be. So these are metal, kind of like nuts, that you heat up with a soldering iron and you push into your part. Awesome, you should definitely get some if you're not using them. This shows stresses over time and cracks that form. The one under it is a connector that's just broken. It's been loaded and stressed over time, and it's just broken. So this will happen with plastics. They're just going to continue to move over time and eventually break. PLA is awful with this. This is like, I love PLA. I think it's great. If you have a part that needs to be under a continuous loading, do not use PLA. It's going to be terrible for you. It's going to, so you make a bolted junction, and you're going to come back in 3 weeks, and you thought it was tight, and it's not tight anymore. That's because the material is crept. If you look at some of the 3D printers around that are printed in PLA, particularly like the belts, or the mounts for the belts, you'll see that those parts have generally kind of buckled and moved in a lot. I'm guessing those people are finding they have to frequently tension their belts. That's because it's kind of PLA being PLA. And so to consider here, this is a place where adding fillers into the material does tend to impair that. So, we talk about, I put carbon fiber in my plastic. Now my plastic is stronger. Well, no, it's not. It's probably not stronger. Maybe it's weaker, but it will be more resistant to creep. So that's something to consider. All right, so my last slide, and then you can ask me questions or mostly just be done with me. So think about this. Keep it in your head as you do your design work. When you're designing for an FFF process, your process, your slicer is part of your design. You're not done when you leave CAD. You're continuing to design when you go into your slicer. So if you're using someone else's profiles, if you're not previewing your parts, if you're not changing your slicer settings every time, you're probably not doing it right because you are not done designing. Next one, never forget, chamfers or fillets, always every single thing that you design. Consider load distribution. Pick the right material for your project. The right material for your project is available at PrintedSolid.com. But in all seriousness, we do carry a lot of materials, but we don't carry every material. And if you want to check in with me, I'm always glad to give what I think is decent advice and guide people towards materials. Now, when I get people calling me a lot of times asking for guidance on a material we don't carry, then we start carrying that material. But until then, if someone calls me and once a year I get a call for some like PEEK, we're probably not going to carry it, but I'm glad to refer you to someone else who does. So, that's all I have to talk about. Does anybody have any questions? Okay, thanks for sitting through me talking for a while, and our booth is over there if you have any other questions. So, thanks. I have time to answer a question? Okay, so the question was, when our school is looking to get a 3D printer, are we going to have a lot of waste material? How are we going to dispose of it? No good answer for you. So the material that you are probably going to use the most is PLA, which is generally not accepted into recycling streams. It does break down over long periods of time under the right conditions, so it's generally considered to be a little bit more environmentally friendly, but that is an area where 3D printing is not great yet. But when you say, am I going to have a lot of waste material, that's a relative question. So we do a lot of laser cutting. We buy about 2 tons of acrylic, say every couple weeks, and we fill up a small dumpster of our waste material every week. Now I do a lot of 3D printing as well. I will fill up a small garbage can every year. So more material is relative. Now, especially when you're learning, you're going to be creating a lot, but it's considered to be, it's an additive process. You're generally not wasting a lot, but you will have some waste. Yeah. All right. Where should I put this?